This video is the introduction to chapter 5.3. Have your note sheets ready. Have the book open also. That would help you as you go along through this. Um, so we've been discussing probability. Now we have another situation called the multiplication rule, and that's going to occur when we're talking about events happening one right after the other, or related events occurring, or we have a sequence of events that occur. And so we'll, instead of doing addition rule, we'll be doing the multiplication rule. And this is going to be related to some ideas of whether events are independent or dependent. And so here are some examples here of some situations that you can look at and read. So I'll let you do that real quick. I'm going to pause, but do that. Okay, now that you had a chance to read each of these situations, let me define this idea for you that we're talking about here. It's called independent events. Two events are independent, not related to each other. Independent. If the occurrence of one event in experiment does not affect the probability of the other, two events are dependent. If the occurrence of one event in a probability experiment affects the probability of another event. And so you read those as some examples to give you an idea. Another idea I have is thinking about, think of the events of your mother getting mad at you and the event of making a bed. Are those independent events? The probability your mom gets mad at you does depend upon what will change depending on if you make your bed or not. So those are not independent events. One definitely has an effect on the other. And so looking at that situation, we have to think about that in terms of when we apply the multiplication rule in certain situations. And so we're going to be talking about those ideas of independent events or dependent events, and how that relates to how we solve these problems where we have these sequence of events. So for example, another gambling example, computing probabilities of independent events where they're not related. One event does not affect the probability of another one. Um, and so I think to kind of solidify, before we do that example, I wanted to show you from the book, this one right here, in other words, to really kind of solidify that. In determining whether two events are independent, ask yourself whether the probability of one event is affected by the other event. For example, what is the probability that a 24-year-old male has high cholesterol? What is the probability that a 24-year-old male has high cholesterol given that he eats fast food 4 times a week? Does the fact that an individual eats fast food 4 times a week change the likelihood that he has high cholesterol? If yes, the events are not independent, or they're dependent. And in that case, I would say those events are not independent. So let's look at an example. In the game of roulette, wheel has slots numbered 0 to 0, 0, 0, 1 through 36. A metal ball rolls around a wheel until it falls into one of the numbered slots. What is the probability that the ball will land in the number slot of 17 2 times in a row? So that it will land on 17 and on 17. That's the situation. If you're not familiar with roulette, here's a picture of it. I'm going to show you that so you can see the game. There it is. There's American roulette. And what you do is you just bet. So I have $1,000 according to this. Here's $1,000 cash. And you just bet on numbers. Let's bet 14, 32, 11, 7. I'm going to bet $1 in each of those. That those are going to come up. And then you spin. Let's see if I win. It gets spun, the ball lands, and it hit 21. 21, I didn't win because I picked those numbers. And so the question on here is, what's the probability it lands on 17 twice? And so what we do is, at the count up, there's 36 slots, 37, 38 different locations. Let me bet 17. Let's see what happens one more time. And so what's the probability it's going to hit a 17? Mathematically, it's 1 out of 38. And then the question is, what's the probability that it happens twice? And so in this case here, there's 38 slots. So what we know is the probability of just 17 on its own equals 1 out of 38. And so then we have a formula down here that we do. If two events are independent, then the probability E and F equals the probability E times the probability F. So in this case here, rolling a 17 on the first one and then on the second one, those are independent events. The wheel doesn't remember what the history is. And so it's just a calculation like that. It's just the multiplication rule. That's it. So it's 1 out of 38 times 1 out of 38. The 38 again because there's 38 slots, 38 numbers. And so that's an application of independent events, the probability using the multiplication rule. And that's the formula we're going to use and apply for this. Let's do one more right here before we finish this video here. And it's the multiplication for a whole bunch of events. I call this, and you'll hear me in class when we go over this, I call this a sequence of events. A sequence of events. That's what I call that. And so the probability of, if they're independent, right, they're not related to each other, it's just the multiplication of all of them. The probability that a randomly selected 24-year-old male will survive the year is 0.9986. So this is related to life insurances, and insurance companies have they have probabilities of if someone's going to survive a year at what age. So it's almost 99.86% that a 24-year-old male will survive the year. What is the probability that 3 randomly selected 24-year-olds will survive the year? So on part A, the question really is that what's the probability that you have 3 males survive, that a 24-year-old male survives, and another 24-year-old male survives, and another 24-year-old male survives. And so that's a male right there. And so it just becomes one of these, a product, a sequence of events that all 3 of them survive. And so the answer would become 0.9986 times 0.9986, 0.9986. And a shortcut you are going to see in the book is 0.9986 to the power of 3. We use exponents on these sequence of events, especially if it's the same value we're multiplying. And so with that there, the probability that 3 24-year-old males will all survive is going to be 0.9986, 0.9986 raised to the power of 3. And so it's 99.6%, pretty much, 0.996. So it turns out to be 0.996. So pretty much assured that all 3 are going to survive. And then let's go ahead and look at part B now. Looking at part B, what is the probability that 20 randomly selected males will survive? And so it's the same problem. It's just we're going to end up doing it 24 times. A 24-year-old male and another one. So you're going to do that 20 times. That 20 randomly selected males would survive. And so following the pattern here, what we end up with is, oops, wrong pen, is a 24-year-old male is going to be 0.99. So I can write this 20 times, or remember that that's just repeated multiplication. And then we can calculate that. So that's going to be 0.9986 raised to the power of 20. And so the probability that all 20 of them survive is going to be 0.972. So still 97% chance that all 20 of those males will survive that year.